In this video, we're going to look at some examples of determining the shapes of molecules. So the first one we'll look at is carbon tetrachloride. Now, in order to determine the shape of a molecule, the first thing you need to do is draw the Lewis structure. In the interest of time, I'm not going to go through the steps of drawing the Lewis structure. I'm just going to give you the final result. If you need more help drawing Lewis structures, please go back and look at my video specifically on drawing Lewis structures. So here's the Lewis structure for carbon tetrachloride. In order to determine the shape, I need to know how many electron groups there are around the central atom. An electron group would be defined as a lone pair or a single bond, double bond, or triple bond. And it doesn't matter whether it's a single bond, a double bond, or triple bond, it only counts as one electron group. So when I look at carbon tetrachloride, I'm only interested in the ones around the central atom. So I'm only interested in what's around carbon. I don't care what's around the chlorines. Right? So the electron groups around the carbon are 1, 2, 3, 4 single bonds. And so I've got 4 bonded atoms and no lone pairs. All right, and so then what we do is look at the different types of geometries that are possible. So this is a table from your textbook. Right, and so this is information that you're going to want to have memorized in order to answer these questions. Right, and so if I have 4 electron groups, then that electron geometry is always tetrahedral. And if I don't have any lone pairs, then the molecular shape is also tetrahedral. So I go back to carbon tetrachloride. So the electron geometry is tetrahedral, the molecular shape is tetrahedral, and the bond angle is 109.5. And one thing that's important, especially when we start talking about molecular polarity, is to be able to picture what these molecules actually look like in your head. Right? So a tetrahedral molecule is not this sort of planar, X thing that the Lewis structure looks like. It actually looks like this picture that we have here, where it's actually has 3-dimensional shape, right? So I've got sort of 2 atoms pointing in one direction, and I've got 2 atoms that are sort of in a plane perpendicular to that. Let's get another example. So here's phosphorus trifluoride. So again, I'm just going to give you the Lewis structure. And now, when we look at the number of electron groups here, remember, a bonded atom or a lone pair counts as an electron group. So this lone pair counts as one electron group. So it has 1, 2, 3, 4 electron groups. 3 of them are bonded atoms, and 1 of them is a lone pair. So if I go back to my chart, right, again, I have 4 electron groups. So the electron geometry is tetrahedral. But now that I have 1 lone pair, right, essentially I pluck off one of those atoms, and so there's just sort of a lone pair there that we can't actually see, and we call this molecular shape trigonal pyramidal. So my electron geometry is tetrahedral. My molecular geometry is trigonal pyramidal because I have this lone pair, and then the bond angle is still 109.5. And again, it's important to think about what the 3-dimensional structure of this molecule actually looks like. It's not this T-shaped thing that we have in the Lewis structure, but in fact, right, it's sort of this 3-dimensional. We get the name because it kind of looks like a pyramid. All right, and finally, we'll look at ozone. So here's the Lewis structure for ozone. Now, when I'm counting the electron groups, the lone pair counts as 1. This single bond counts as 1. And this double bond just counts as 1. So it doesn't matter that it's a double bond. There's only 1 atom that's connected to the oxygen by that double bond. So double bonds only count as 1 electron group. So the central oxygen atom has 1, 2, 3 electron groups. Right? 2 of them are bonded atoms, and 1 of them is a lone pair. So if I go back to the chart, 3 electron groups, the electron geometry is trigonal planar. But when I have 1 lone pair, that molecular shape is bent. Right? And you can see, right? I mean, the names of the shapes are actually trying to be descriptive of what the molecules actually look like. So for ozone, the electron geometry is trigonal planar, the molecular geometry is bent, and the bond angle is 120 degrees.